Welcome back. All right, welcome back to this YouTube channel. So in the last video, we have I think we have covered some evaluation metrics over the last few videos. I think last two videos, we have covered some evaluation metrics. So how can we evaluate how good our object detection model is? So in this video, we are going to look at some we are just going to look at the basic process, all the process that we have to do that we have to do in order to build a RCNN, regional CNN model for object detection. Right, so we'll just do this. Right, I'll just back. So RCNN from scratch. So first of all, as I have already I think I have already told you about this RCNN in the first video, Introduction to Object Detection, right? So I have already told you what is the overall structure, what is the overall like how the model works on overall. So in this video, we are going to cover it in I'm just going to cover it again in a specific video, and we are also going to look at some code snippets, look at some codes that I have wrote. Now we'll just try to understand what is happening in that code, and then hopefully we'll carry on, right? So first, we have RCNN, right? So first, I'm just going to talk about the process. Sorry, right? And the process, which is the process. All right, how to build a RCNN model? All the steps that you have to take. So first, as you might have known, as you will know, if you have been following machine learning and deep learning, uh, either along with me from the beginning, or if you have any intuition of machine learning, we have training data and testing data, right? So what is a training data in the case of object detection models? Well, let's say the training data is some images, right? Let's say you want to classify between detecting let's say we just want to detect faces, like we just want to detect faces and nothing else, right? So we just want to detect whether a we just want to detect whether a face is there at a particular part in this uh, image, and then we want to locate it, right? So I'm just going to say the inputs is the image. We have the same image as the input, and then what is output? What is output? The output is the coordinates, right? So we'll just have the coordinates of the bounding box. Let's say I have this frame, my frame as the image. We're going to have some coordinates of a rectangular box or any type of box that can capture the location of my face, the overall location of my face. So this is the input, and this is the output of the model in general, right? And then we are going to see how we can what are the process first for the training process that we have to do. So in order to train the model we have to train the model. In order to train the model, the input to the model is, so what will the model get? Well, the model will get segmented parts, right? So the model will get and what should the model predict? Well, the model should predict, right? Model, it will be passed to the model, and then the model will predict the how good this segmented area is. So it'll actually predict how good the segmented part is, right? So how accurate is the segmented part closer to the actual detection, right? So it is going to just validate it, and we're going to get, let's say, an IOU score. So what are we essentially doing is we are going to calculate the IOU score between segmented part that is given to the model, and then the actual box. While training the model, we don't know what is the actual part. Sorry, while training the model, we will know what is actual um, actual location of the object is. So we'll just get a square as the actual location, and then we are going to update this model's weight such that the models predicted, let's say, uh, yeah, the model should predict that the IOU score, that the model should predict if the IOU score will be greater than a threshold, let's say 70%. So if the IOU score is greater than 70%, then it is a yes. If it is less than 70%, then it is a no. So what we are going to do, so that is the major functionality of this model. So while training, so what is the loss function? Well, the loss function is just the prediction of IOU score, the difference of IOU scores. So we are going to have this IOU score, actual IOU score, between the detection. So this is actually not IOU score. The better word to describe it is just a prediction, right? It's just prediction of how good the segmented area is, how close the segmented area is with the detection, which we will not know while predicting, but will update the parameters based on loss function, right? So that is the thing, right? IOU, right? So what should be passed to the model? What should be the input of the model? Well, we should first get the segmented parts. So in OpenCV is a library, right? It's a library in Python which is great for computer vision tasks. If you want to do any type of computer visions, object detection and all that, you can do. You can use a library called OpenCV. I am also going to cover that in the future videos when we are developing YOLO and all that. So we have this segmentation algorithm that is already pre-written in in OpenCV library. So you can just use this segmentation algorithm that is wrote by the OpenCV library. We can use it to we can just input the image and then we'll get some random segmentation. So not random, but some possible predictions, right? So we are going to get some possible uh, detections, and then we are going to pass each detection to the model, and the model is going to predict how good the segmentation is or how good the predicted box is, and then we are going to and then we are going to compare it with the actual value. The actual value, how are we going to get the actual value? In the training data, we already will have the labels, right? So we are going to compare that segmentation parts, the input of the model, with the actual IOU that will calculate, and then based on that, we'll update the model's weights. So you are going to understand this better when we are when we are going to read the code, right? So that is what we want, and I also want to share a newer model, faster RCNN, fast RCNN. Fast RCNN. So it is just another type of RCNN in which you will just add a max pooling lever. So what is the idea of this fast RCNN is? I'm just going to elaborate in simplest terms. Right? So as you know, in the model part, the model will receive segmented areas, right? So in fast RCNN, we'll just use a max pooling layer to further convert this segmented areas into smaller images, right? So we're just going to convert this bigger segmented parts into smaller parts. So that is the idea of RCNN. And now I think you have understood the idea of RCNN, so how idea process of building an RCNN, right? How can you, like, what are the process that you have to do in order to develop a RCNN? Now let's look at some code. Let's read. Let's read some code. Let's see how we can develop a RCNN from scratch. First, as you can see here, we'll import some necessary libraries, right? So we have some of these necessary libraries that we are going to use in the future. So we have OS, right? So OS is, in order to access local directories, we use OS, and then we have CV2, which is nothing but OpenCV, right? We have open CV2, which is nothing but OpenCV, and then we have Keras TensorFlow, right? So it's just the backend of TensorFlow. I think, yeah, sorry, it uses the backend of TensorFlow, and then we have Matplotlib.pyplot. If you want to plot these images, or if you want to see these images, then this is a great library. And you know NumPy, right? We have been working with NumPy. So NumPy we'll also use NumPy, and then we'll use TensorFlow. And then as you can see here, this lengthy function, right? So this is the class, right? We have this class, and then this function, this lengthy function is the function to is the function that will generate the segmentation parts. So let's propose some segmentation parts to the model, and then the model is going to rate how good this segmentation parts is. So if we can first we'll create an object of this class, right? So we'll create an object first, and then we are going to run it in the future. And then we have this function get IOU. So we are going to calculate the IOU. So first we're going to calculate the like the so the input. As you can see, what are the inputs are, we have two bounding boxes. bb1 specifies bounding box 1, and bb2 specifies bounding box 2. And then we are going to have these values. We are going to calculate the leftermost value between the x1 coordinate of bb1 and bb2, and then we'll do all these things as you can see here. And then we have condition here. So what this condition is specifying is that if both of these bounding boxes doesn't match up, right, so they never intersect, then it is zero, right? So we are just going to check for that condition. If this is the case, if this condition is true, then we are going to return zero. And then after that, we are going to calculate the intersection area. That's the area of intersection between these two boxes. And then this is the thing. This is how we calculate it. And then we'll actually calculate each box area in order to calculate the union, right? So this is the intersection, and this is the union. The sum of both of these values is the union. And that is what we do here. We'll just create a variable IOU, and then we are going to say intersection area divided by the float of bb1 area and plus bb2 area. And then finally we are going to return IOU. And then this thing here is the this part of code, this cell of code we use to generate a trade images, this new cell of code. Let's see what is going to happen, what is happening here. We'll first initiate tool list here in order to sorry around that, no problems. So we have created these two variables to store the image values and labels. And so what we'll do is, so this annotation, so this variable or this value is nothing but the label values, right? So all the detection points. So as I have told you here, so what are the output labels? So what should the model predict? Well, we'll have coordinates, right? So we'll have 4 coordinates determining the location of the box. So where the box should be and size of the box and etc. So we have 4 coordinates that are going to specify the shape of that box or the location of the box. And then right, so that location is stored in a, let's say a folder here, annotation. And then what we'll do is we'll just here I have run it on an airplane data set. So I'm just going to say I'm just going to loop through. So I'm just going to uh, go through this, right? You don't need all of this, because in this video we are only looking at the architecture implementation, how we can implement the models. But you know, this is just for like you can use this model for any type of data set that you want. Go to just go to kaggle.com. I think I have already shared it with you, kaggle.com. Just go through it, and you know, you'll find some great data sets to apply these models. Let's here see what will happen. I have defined another variable df, which shows the um, detection points for each. So we'll loop through all of these detection points, right? So for each detection point we are going to get a data frame. And so we are going to, so data frame is another object of pandas. Like we can just create data frame, something called data frames, which can show data for you. And then we are going to create another list dt values, and then we are going to loop through each of these data points. So what is the output of so for each image, for each row, we are going to have 4 values, right? x1, y1, x2 and y2. So we are going to extract these values, and then we are going to append these values as a dictionary to this where to, right, to this list. So we are going to have this gt values list, and then we are going to append these values, right? So the values of x1, x2, y1, y2 to this list. And then this is the part where we, so these 3 lines of code, we use these 3 lines of code to generate this segmented part. So we'll have this image, and as you can see here, that's, so we'll have this image, and then we are going to run it through the segmentation algorithm in order to get the segmented parts, proposed segmented parts. And then we are going to have some counters here. So we are going to have some counters. These counters help in regulating the number of data points that you want. Let's say if you only want 2000 segmented parts, then it is going to control how many segmented parts you want, how many inputs and outputs you want. And then we have another flags determining how many positive and negative samples you want, right? So in order to, like, if you want to build a machine learning model, a powerful machine learning model that can perform good, you should make sure that the positive and negative examples are approximately of equal number. So let's say, I'm just going to give an example. So let's say I want to build a classifier between my face and another and another face. You want to make sure that you provide equal number of faces of me and that other person, such that the model can really learn the difference. So that is why, in order to regulate the number of, in order to approximately equalize the number of positive and negative samples, we'll use this flux. And then you can see here what we are doing. We're just going to yeah, so as you can see here, and then we are going to loop through this gt values are nothing but the coordinates, right? So the actual coordinates, the target coordinates. And then we are going to loop through this, and then we are going to calculate the iou between the gt values and the predicted segments. And then if the iou is greater than 70%, and then we are going to append this image to this train image list, and then we are going to append one to this train levels, because the iou is greater than 70. So if the iou is greater than 70, then we are considering it as the right answer. So therefore we are going to add it to this train levels. And then we're going to increase the counter in order to track how many number of samples we have. And then we are going to do the same thing for the negative samples also. We are going to calculate if the iou is less than 30%. If the iou is less than 30%, then we will consider it as a negative sample. That is, there is no bounding box. And then, as you can see here, we'll just convert these images into numpy arrays in order for us to build this model in TensorFlow. And then we'll import some TensorFlow libraries. We'll import vgg16. So vgg16 is nothing but a simple fully, like, feed forward network. We'll have many number of layers in this vgg. I think yeah, it is a CNN layer, and it is a classic CNN architecture, and but we'll have much deeper number of layers. And then we are going to get the first 15 layers. Yeah. And then we are going to set trainable equals false. We are not going to train the model while training. And then we are going to build the model is, the input is vgg model.input, and we are going to get the predictions. So as you can see here, we can just put in one and soft sigmoid here. But like, for you to understand that this model is scalable for many number of classes, I'm just going to put here, I'm going to use softmax activation function. So we have two neurons, and then we have softmax that is the neuron that will light up will have the actual correct value. And then we are going to use Adam optimizer with a learning rate of 0.001, and then we'll compile that using categorical cross entropy. Then we are going to fit or train the model. So I hope you understand what is going on here. I will just look at this code and try to read through it, try to get some understanding of it. And in the next video, we'll look at the YOLO algorithm, right? So you only look once algorithm. This algorithm is the state of the art models that is used in the field of object detection. There's a new model that came also, like, recently, YOLO 8 and YOLO NAS. We are also going to look at that. And then, yeah, thank you for watching, and see you in the next video.